In this video I am going to discuss about irreducibility in polynomial ring. So first of all we need to know the definition of irreducible polynomial. That's why I have given the definition. Here you can see, suppose we are considering some integral domain D, then a polynomial px which can be taken from D adjoint x, you can consider or you can pronounce this one as D adjoint x, is said to be irreducible polynomial whenever we can write px in the form of fx into gx. Then the condition is that either fx or gx should behave like a unit, or in general you can consider it should behave like a constant polynomial in D adjoint x. In simple words, if you want to consider the structure is what? Reducible. I am saying about reducible. Then you can imagine the structure should be factorized into two linear factors. Whenever you are considering any expression, if you can factorize it within a certain specified domain, then you can simply call it reducible. Otherwise you can call it irreducible. So here this is the formal definition, but for your own convenience you can remember in this way. If you can reduce it or if you can factorize it within the given domain of definition, then it will be reducible, otherwise it will be irreducible. For example, you can consider this note also. If we consider a non-zero non-unit polynomial of D adjoint x which is not irreducible, that means if it does not satisfy this criteria, then definitely we can say it is reducible. Now for example, I have given two specific examples in order to explain this one. You can understand the first one. X square plus 1 is irreducible over R, but it should be reducible over the complex plane C. Why? Because if you consider the factorization of x square plus 1 equal to 0, then obviously the possible structures are x equals to plus minus I. So definitely you can understand there does not exist in real number which has the value plus minus I. So definitely it belongs to C. So if I ask you what are the factors of this expression, one is x minus I, second one should be x plus y, and consequently you can say the factorization is not allowed in terms of real plane, but whenever you are considering the complex plane, definitely this type of factorization is allowed, and hence you can say the structure is reducible over C. Remember I told you reducible means, in simple words, within the domain of definition or within the domain under consideration the structure should be factorized. This is the simple implication. And if it is irreducible, definitely there are technical definitions, but main fundamental fact is that you cannot factorize it. Here again, for better illustration, I am giving another example. Suppose we are considering x square plus 1 and I am claiming that this part is irreducible over z3, but it should be reducible over z5. I have given another alternative technique in order to check this one whether it is irreducible or reducible. Now we all know what is the meaning of z3. It should contain three residue classes, technically 0 bar, 1 bar and 2 bar. So fx can be considered as x square plus 1. What you have to do, simply you have to put 0, 1 and 2, better to say 0 bar, 1 bar and 2 bar in this expression. Now if you put x equal to 0, that will be 0 square plus 1. So simply you can consider this is equal to 1. Now if you put x equal to 1, it will be 2, that means outcome will be 2 bar, because we are concerned with the residue classes. If you are putting x equal to 2, then it will be what? 2 square 4 plus 1, 5 bar. But actually you are considering what? Z3. And if you are considering Z3, then you have to take the modulo 3 because it is greater than 3. So remainder term in case of 5 will be what? 2. So f of 2 bar will be equivalent to 2 bar. So here you can see f of 0 bar it is not equal to 0, f of 1 bar it is not equal to 0, f of 2 bar it is not equal to 0. So 0 bar, 1 bar, 2 bar, none of them will behave like a root of this expression under Z3. But if you get any particular expression is equal to 0 bar, then the same thing can be expressed as a root of the given expression, and consequently you can say there must be a factor so that it will behave like a reducible one. So in general, as 0 bar, 1 bar, 2 bar is not a root of the given expression fx, that is supposed to be x square plus 1 over z3, so definitely we can say it is irreducible over z3. Now the scenario will be totally changed if we consider z5, because in case of z5 you can see the 5 possible residue classes are given by 0 bar, 1 bar, 2 bar, 3 bar and 4 bar. So here again you can find out f of 0 bar is equal to this, f of 1 bar is equal to this. I am not saying the value where how it will come, because you can easily put these values in the given expression x square plus 1 and you will get the result. F of 2 bar is 5, but because you are considering z5 right now, take modulo 5. So 5 when divided by 5 gives you 0 remainder, so it will be equivalent to 0 bar. F of 2 bar is also in a similar fashion. F of 2 bar is equal to 0 bar in this way. So here you need not to proceed towards 3 bar or 4 bar, because what is my objective? My objective is to show it is reducible or irreducible. So already I have obtained one root. F of 2 bar is equal to 0 bar means as if you are putting x equal to 2 in this expression and you are getting 0 whenever the domain is z5. So technically x equals to 2 bar can behave like a root of x square plus 1 in z5. Now simply use the concept of classical algebra. Whenever x equal to alpha is a root of fx equal to 0, then definitely you can say x minus alpha is a factor of that expression. So here also we are getting the same thing. X equal to 2 bar is a root of this expression. What does it mean? X minus 2 bar can behave like a factor of this expression, and hence definitely the structure can be factorized within z5, and so that you can say x square plus 1 is definitely going to be what? Going to be reducible over z5. So in this way you can easily verify whether the given structure is reducible or irreducible. Now I have stated two specific results without proof, because proofs are not important in case of competitive exams. That's why I am not explaining the proof, but you can remember these two results. To some extent they will be useful. Now first result states that only possible irreducible polynomial in R adjoint x are nothing but the linear polynomial. Obviously linear polynomial means you can consider the shape of the polynomial as ax plus b, or the polynomial of the form x square plus ax, or you can also consider x square plus bx plus c or minus bx plus c, satisfying this criteria, b square minus 4c less than 0. In some other videos I will explain how to implement this result. Now in the second result I have mentioned the only irreducible polynomial in the complex plane can be considered as linear polynomials. That means specifically it can be considered in the shape of ax plus b. So again I am saying whenever you are considering the structure is irreducible, then px should be written in the form of what? Fx into gx. Either fx or gx should behave like a unit, that is constant polynomial. Or in simple words you can consider whenever the structure is reducible, then you have to split the original expression in the form of what? In the form of two factors. At least two factors will be available, as you can reduce it to the lower degree polynomial, so that's why it is called reducible, otherwise it will be irreducible. Now there is a very important result related to reducibility corresponding to any polynomial having degree 2 or 3. You can consider this example, or better to say first you can consider this article. Again I will say I am not giving the detailed proof of this result, because proofs are not important for competitive exams. Simply I am giving the outline of the proof. Now the result is very important, so let us consider the statement of this theorem. Let f be a field and fx belongs to f adjoint x, that is this is the field of polynomials, and degree of fx is either 2 or 3, then fx is reducible over f if and only if fx has a 0 in capital F. That is very much similar to the previous criteria by means of which we have solved the example. So if possible, let us assume fx can be written in the form of fx gx into hx, where gx into hx belonging to what? F adjoint x. Now degree of fx can be written as degree of gx dot fx. Now degree of fx as per our condition either 2 or 3. So one of the polynomial, it may be gx or it can be hx, must be of degree 1. Suppose gx is degree 1, then hx is of degree 1, so that the totality of degree will be 2. Otherwise any one will be 1, otherwise so that the other will be 2. So again degree will be 3. So one of the polynomial, it is certain that its degree is going to be 1. So if possible, let degree of gx is equal to 1. That means it is going to be a linear polynomial, so that we can say gx can be written in the form of ax plus b. Now just by observation you can understand, if you put x equals to minus ba inverse, then the result will look like this: a into minus ba inverse plus b. That means minus b plus b, because a inverse ultimately cancels out to give you identity, so it will be equal to 0. So x equal to this belonging to the field is definitely going to be a root of gx, and consequently fx can be written in the form of a gx into hx, and hence any root of gx is definitely going to be a root of fx. So this shows fx must have a root or 0 in f whenever we are considering this type of structure. Conversely, if we consider fx as a root alpha in f, then definitely we can write fx in the form of what? X minus alpha into gx. That means I have taken this one in the form of linear polynomial. Now suppose fx is of degree 2, then gx is also having degree 1. If fx is of degree 3, then gx degree will be 2. So technically you can understand fx is reducible in this case. So that means whenever we are considering degree of fx is 2 or 3, so definitely it is going to be reducible over the field f, provided condition, in fact it is a necessary and sufficient condition, that it should have a 0 in f. Now when you can use this result in a particular case, here I have mentioned that one, you can use the above result particularly for zp, because in this case we can check the reducibility of fx by checking f of a equal to 0 or f of a not equal to 0. Just remember this example. Here we have used all possible residue classes to put in the form of x, and whether we have checked whether the value is 0 bar or not. So here also f of a equal to 0 or f of a not equal to 0, that is the main important part. Then there is another note, the polynomials of degree having more than 3, larger than 3, may be reducible over a field even though they do not have zeros in field. That means whenever you are considering any polynomial whose degree is higher than 3, it is not mandatory that you have to apply this result. In those cases this result may not be true. For example, I have taken the example of q adjoint x. Suppose I am going to consider any certain polynomial x to the power 4 plus 2x square plus 1. Obviously you can consider this structure is written in the form of x square plus 1 equal to 0. You can clearly understand this part can be written in the form of x square plus 1 into x square plus 1. That means you can consider factorization of this one, but technically it does not contain any 0 in q, because whenever you want to find out the 0, it will give you plus minus I. So this result is specifically valid for any polynomial whose degree is either 2 or 3. Now we have another important definition, that is known as content of the polynomial or content of polynomial. You can consider any non-zero polynomial. For several times we have used the general shape as a n x to the power n, a n minus 1 x to the power n minus 1 plus dot 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 a naught. Obviously I belongs to z. Now let us find out the greatest common divisor of all these coefficients. Now this greatest common divisor of an minus 1, an minus 2 dot 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 a1 a naught should be obtained. Then the content of the polynomial of this non-zero polynomial in fact can be defined in this way. That means simply you can remember content of the polynomial is nothing but the GCD of the coefficients of any non-zero polynomial, where coefficients are given by means of a naught, a1, a2 dot 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 an. Again there is another important definition, and this definition belongs to primitive polynomial. You are considering any polynomial of this shape where ai belongs to z as usual. If its content is equal to 1, GCD is equal to 1 for all this coefficient, then you can say it is a primitive polynomial. Here again for your convenience I have given some important results which can be used for solving different problems. For example, two primitive polynomials can be taken, then their product is also primitive. Second one is what? Fx belongs to z adjoint x, then fx is reducible over q. Suppose it is given to you, then it is definitely reducible over z. Sometimes we can use this criteria in order to solve different problems. And the third one, suppose we are considering p is a prime number and let fx belongs to z adjoint x such that degree of fx is greater or equal 1. That means it can be a linear polynomial or it can be more than that. Now we are considering another polynomial given by f bar which can be obtained from fx. Obviously it is a part of zpx by reducing all coefficients of fx modulo p. That means it can be obtained in case of z3. It can be obtained by reducing all polynomials with the help of modulo 3. In case of z5 it can be obtained all coefficients of fx with respect to modulo 5 and so on. Now if you can show that fx is irreducible over z5 and degree of f bar x is equal to degree of fx, then definitely the structure f bar x is also irreducible, fx is also irreducible over what? Q. That means irreducibility of fx over zp. Along with this condition, ultimately implies irreducibility of fx over q. Now let us illustrate by means of an example. Suppose fx is given by this structure. Here you can see 21x cube, 3x square, 2x plus 7. Now we are considering z2. Now remember, I told you have to reduce all coefficients of fx under zp with respect to modulo p. So f bar x will be what? Apply modulo 2 over 21. What will be the result? Remainder will be 1. So 1 into x cube, that is simply x cube. Now 3x square, again apply modulo 2. 3x square, 3 divided by 2 gives you remainder 1. So that means x square. 2 divided by 2, remainder 0. So this part will be abolished. 7 divided by 2 will be, obviously remainder will be 1. So ultimately f bar x, after reducing with the help of modulo 2, because we have taken z2, can be written in the form of x cube plus x square plus 1. Now you can consider f bar 0. What is the meaning of f bar 0? Putting x equal to 0, you will get some result. F bar 1, that is also you have obtained this type of structure. Now here you can consider f bar 0, f bar 1, that is equal to what? 1. That means f bar x is irreducible over z2. Why we are putting only 0 and 1? Because you are considering z2. So only two possible residue classes are available. One is 0 bar and another one is 1 bar. Now here, as you have obtained, none of them is equal to 0. So that's why you are saying the structure is irreducible over z2. And also you can understand degree of fx is what? 3, and degree of f bar x is, that is also 3. So degree of f and degree of f bar, these two things are identical. Then by the previous condition we can say fx must be reducible over q. Initially it was irreducible over zp, fx is irreducible over zp, that is over z2. Now it is also irreducible over q. Now in this way you can utilize this criteria to solve the, or better to say, to check the irreducibility of any given structure. Now we have the very important Eisenstein criteria. We all know this. In MSc first semester you must have done this one. So fx is, as usual, the general shape of a polynomial. Now let us consider a certain prime p such that p is not a divisor of an, that is the leading coefficient, but it should be a divisor of all other remaining coefficients. But at the same time p square should not divide a naught. Then you can say fx is irreducible over q. Now this test can be conducted in order to check the irreducibility over q. Now associated to Eisenstein criteria, there is another important fact, or better to say another important structure, which is known as cyclotomic polynomial. Now suppose we are considering the pth cyclotomic polynomial, that is usually denoted by phi of px and can be expressed in the form of x to the power p minus 1 by x minus 1. Now you can factorize this one to get this type of structure. Now this part is irreducible over q. Now how to justify this part is irreducible over q? For that purpose, suppose we are considering a new structure fx given by phi p of x plus 1. So what does it mean? X should be replaced by x plus 1 in this expression. Now x plus 1 whole to the power p, with the help of binomial theorem you can easily expand this one. Then minus 1, in the denominator portion you must have x plus 1 minus 1, because x has been replaced by x plus 1. Cancel out 1, so you will get x. Now divide the entire expression by x. Already you can see 1 and minus 1 will be cancelled. So x to the power p minus 1, px to the power p minus 2. Continuing in this way, the last term should be what? Px by x, that is p. Now here you can easily understand p will divide all possible coefficients of fx except the leading one, because everywhere p is available. So leading coefficient has 1, so technically p cannot be a divisor of this expression. Also you can understand the last constant term is p, so p square cannot divide the constant term. Then by Eisenstein criteria we can say fx is irreducible over q. Now if possible, phi x can be written in the form of hx into gx. Suppose this is a non-trivial factorization of phi px over q. Then fx will be like this: phi px plus 1, that is gx plus 1 into hx plus 1. That will be again a non-trivial factorization of fx. But if this is possible, this is technically absurd. Why? Because already we have explained phi px is irreducible over q. So if I ask you, whenever the structure is irreducible, how to justify this one? you can prove up to this one, and this is the proof of irreducibility of pth cyclotomic polynomial. Now you will find these definitions pth cyclotomic polynomial in any standard textbook of abstract algebra. Then there is a note: the irreducible polynomial plays exactly same role as prime number plays in case of integer. I have given this one to understand the homogeneity of these two terms. Whenever we are using the concept of prime in case of integer theory, the same thing can be converted in terms of irreducible polynomial whenever we are considering UFT. So actually, in case of fundamental theorem of arithmetic, we have already seen the use of prime numbers. Similarly, in case of UFD, irreducible polynomial can be treated in a similar manner. Now we have a very important result. That's why I have given the proof of this expression also, and also in order to solve different problems, the structure is extremely important. F be a field, Px belongs to f adjoint x, then ideal generated by Px will be maximal in f adjoint x if and only Px is irreducible over f. This is a very important theorem. So now suppose let us consider ideal generated by Px is maximal in f adjoint x. If possible, Px is reducible. Then we can write Px is equal to what? Fx into gx. Px belongs to ideal generated by fx, so that means ideal generated by Px can be considered as a subset of this expression. But technically, Px, ideal generated by Px, is supposed to be maximal as per our assumption. So only one possibility is there: either ideal generated by Px is itself equal to what? Ideal generated by fx. Otherwise, this is the largest possible structure, that is itself it is equal to f adjoint x. So you can see in the next page I have written the same thing, or f adjoint x is equal to what? F equal to ideal generated by x. Now suppose we are considering the first case. If ideal generated by Px is equal to ideal generated by fx, then Px and fx can be considered as associates with respect to each other, and so that you can say Px can be written in the form of fx into gx. Then by the definition of associate, we must have gx is nothing but a unit. Also, if ideal generated by fx is equal to what? F adjoint x, then definitely fx is a unit. So in both the cases, ultimate conclusion is what? Px must be irreducible. Now in the next part, in the converse part, actually we can assume, if possible, Px is irreducible. Suppose we are taking any arbitrary ideal of f adjoint x satisfying the criteria: ideal generated by Px, subset of I, which is a subset of f adjoint x. Now because we know f adjoint x is a PID, so definitely there should exist certain element gx belonging to f adjoint x, such that the entire structure should be generated by what? Ideal generated by gx. So because I is an ideal of f adjoint x, we can imagine I is nothing but ideal generated by gx. So that if this is possible, because Px is a subset of I, that means ideal generated by Px is definitely a part of ideal generated by gx. From this relation you can conclude about this line, so that Px is equal to fx into gx. You can imagine in this way, because Px can be expressed something into gx. Obviously fx is a part of what? F adjoint x. But because Px is irreducible, that means what? Px is equal to fx into gx. This will imply either fx is a unit, otherwise gx is a unit. And if fx is unit, then Px and gx must be associates by definition. And obviously in this case, ideal generated by Px will be equal to ideal generated by gx, and technically that should be equal to I, because simply you can consider this is equal to 1. So Px equal to gx, so ideal generated by Px will be ideal generated by gx. In a similar manner, you can also consider, if gx is a unit, then ideal I should be equal to what? Ideal generated by Px, that is equal to ideal generated by gx, which must be equal to what? Fx. So that means ideal generated by Px is supposed to be maximal ideal. So this is one of the very important criteria by means of which we can easily solve different problems. Now there is another corollary corresponding to this theorem, that is, if f is a field, Px, Ax, Bx all belongs to f adjoint x. Here also you can write this is f adjoint x. Now if Px is irreducible over f and Px is a divisor of Ax into Bx, then we must have either px is a divisor of x, otherwise px is a divisor of bx. Again I am saying I am not discussing the proof of these results. If you require any proof, then you can ask me in the comment section. I will definitely give you the proof in the next video. Now let us solve one such problem using this theorem. We have to show x square plus 1 and x square plus x plus 4 are irreducible polynomials in Z11 adjoint x, and also we have to show these two are nothing but fields having 121 elements. I am proving the first one so that you can try the next one. Now in the first case, fx is what? X square plus 1. Z11, that means how many residue classes are there? Technically 11 residue classes are there, starting from 0 bar to 10 bar. So first of all you have to check whether any of this residue class can behave like a root of the expression x square plus 1 equals to naught. I mean to say f of 0, f of 1, f of 2, f of 3 in terms of residue classes up to f of 10 should not be equal to 0 modulo 11, because in that case it will behave like a root of this expression. So that's why you can see here I have calculated f of 0, f of 1, f of 2, etc. up to f of 10. Now up to f of 3 you can see the value is 10, so there is no use of modulo. But after f of 3, whenever you are calculating f of 4, 5, etc., once you are getting any value which is higher than 10, that is it may be equal to 11 or more than 11, then you have to implement modulo 11 so that the structure will be reduced. So here you can see none of them is equal to 0, so definitely fx is irreducible over this. Now remember the previous criteria. Because fx is irreducible over this structure, then by previous theorem obviously ideal generated by fx must be a maximal ideal, and if it is a maximal ideal, then this particular expression can be a nothing but a field. So Z11 over x adjoint x, you can say factor ideal generated by x is actually a field. So using division algorithm, if possible, let us choose any element hx. So applying division algorithm, what can you write? Because you have taken the structure from Z11 over x and you are considering fx as x square plus 1, so hx must be written in the form of gx into x square plus 1 plus the remainder structure, that is rx. Now here rx is either 0, otherwise rx should be equal to what? 1. So if rx is equal to 0, then we have nothing to prove. Rx is equal to 1 will give you what? Rx is nothing but a linear polynomial. So you can write this one in the form of ax plus b, where a and b both should be taken from Z11. So hx can be rewritten in this form. That means I have introduced ax plus b at the end. So hx plus ideal generated by x square plus 1 can be written like this. Actually you can understand this is also a part of ideal generated by x square plus 1, so that it can be reduced to ax plus b plus this expression. Hence you can say this entire field should contain all the elements of the form ax plus b plus ideal generated by x square plus 1. Now how many possible choices are available for a and b? You can see for a, because you are considering Z11, so technically you should have 11 elements starting from 0 to 10. Similarly from b, for b again you have 11 elements, because repetition may be allowed. So technically 11 into 11, total 121 possible structures are considered in the form of ax plus b, and hence you can say this entire structure should contain 121 elements. So order of this structure should be equal to 121, and hence you can say the required proof is what? This is a field having 121 elements. In a similar fashion you can also prove the next one. Now here I have given another example. You can try to solve this one. 3x square plus 4x plus 3 belonging to Z5x. The factors are 3x plus 2 into x plus 4, 4x plus 1 into 2x plus 3. Now you are asked to check whether Z5x is a UFD or not. So you can consider fx equal to like this: f of 0, f of 1, all this can be calculated. So from this expression you can easily understand f of 1, this is equal to 0, but that means x equal to 1 is going to be a root of this expression. So you can see I have written this one. 3x plus 2 plus x plus 4 can be written in this form. Just multiply this expression. Then using modulo 5, because you are concerned with Z5, you will get this type of structure. 3 cannot be modified. 14 divided by 5 will give you remainder 4. 8 divided by 5 will give you remainder 3. In a similar fashion, you can take the product of this one and you can reduce it after using modulo 5 by means of this structure. That means 3x square plus 4x plus 3 can be factorized in the form of this or even in the form of this. There are two possible representations. Now, as these are the two possible factorized representation of 3x square plus 4x plus 3, now you can also understand with respect to modulo 5, 4 and minus 1 are related to each other. 1 and minus 4 are also related to each other, because 1 plus 4 minus minus plus 5 is definitely related to modulo 5 because it gives you the remainder 0. So multiply the first expression by x. So 4x will be congruent related to minus x modulo 5. Then 1 congruent related to minus 4 modulo 5. Add this 2, you will get this one. That means 4x plus 1 must be an associate corresponding to this structure in Z5. Similarly, you can show 2x plus 3 is definitely going to be a associate corresponding to 3x minus of 3x plus 2 with respect to modulo 5. That means you can say the above factorization is definitely unique with respect to multiplication, and obviously you can understand Z5 is a field, so Z5 adjoint X is definitely going to be a UFT. So in this type of problem, so in this way you can solve this type of problems, and I hope you can, if you can go through this video, it will be beneficial for you. Thanks for watching. If you have any question related to this topic, then you can ask me. Thank you.